Hi guys, good afternoon. So can you just guys confirm participants you are able to hear me and you are able to see my screen as well? Okay. Guys, few more confirmations and we can start the session then. Okay, thank you Bharti ma'am. Thank you Lavanya ma'am. Thank you. So guys, let's get started then. So thank you Giridhara Krishna sir. Thank you. All right guys, so let's get started. Yesterday we were able to understand, right? So yesterday we were able to understand what is the difference between AI, ML, DL. Okay, thank you guys. And one more announcement, guys. So this is still the festival going on. So I wish everyone happy Diwali. Okay. So hope you guys are enjoying your festival as well. So this is one bonus. So this session's gonna be let's imagine this is a Diwali gift from XLR. So and also from the team, obviously the professors and the colleagues. So guys, let's get started then formally. So we were able to discuss yesterday what is the difference between AI, ML, DL, and how to identify these differences. Yeah, thank you guys. Thanks for the wishes and everyone sent to you. So we were able to understand. And guys, don't forget the rule. Just like the yesterday, I wish everyone will be very interacting and very interacting and very enthusiastic, just like the yesterday. And we'll try to make it this session more and more lively. Okay. So guys, we were able to understand. We started with understanding what is the machine learning, what is deep learning, what is AI, what are the differences. And then once we are able to understand how to differentiate between this algorithm, we started with the approach, what is machine learning and what are the different methods, right? So the different methods we were able to understand is supervised, unsupervised algorithm. And we seen something around like reinforcement learning. And then we also discussed that when we spoke about this reinforcement learning, we understood that there is one more method which is called as semi-supervised semi-supervised learning. And this is also a perfect method which corporates always use. It is kind of a hybrid approach, which we were able to understand. And we saw that we yesterday we were able to understand the entire concept, like how this hybrid approach is used. Okay. And then once we were able to understand these things, we started with the introduction. So what are the algorithms available and how they look like? So you can see the supervised algorithm. So we started with the supervised algorithm. In supervised algorithm, before that, we were able to also understand what are my three major tasks, guys. So let it be any kind of a situation. Let it be a AI, let it be a machine learning. Okay. So let it be a data science. So can you guys like, if you could remember what are my three major tasks? I'm talking about the task as of now, right? So we saw the method. Methods are supervised, unsupervised, semi-supervised, reinforcement learning. These are methods. But when I speak about the task, guys, what I told you, what are the three major tasks which I will be performing each and every time whenever I doing machine learning, let it be data science, AI, machine learning, whatever it may be, right? Awesome, awesome. Thara Devi, thank you. So it's the same thing. It's a regression. It's a regression task, then classification task, cool, and the clustering. Okay. Thank you, Nana Priya ma'am. Thank you. Correct. Awesome. Correct answer. Guys, and then I told you guys that how to identify, right? How to identify the difference between regression, classification, and clustering. So when I speak about clustering, guys, what is my end result? If you guys can remember, what is my end result? What I am getting? What is the predictions I am getting here? When I am so I told you that all the time we will be doing predictions only, right? Our job is to do prediction only, right? So when I'm doing prediction, what is the end result I get when I try to apply the clustering, guys? If you could remember, what is the end result of clustering? We saw the detailed example, like what is the difference between clustering, classification, regression with the live example. So guys, can you please tell me like what is clustering? And if we know the clustering, what is the end result? Like what I will be getting in clustering? Guys, come on, fast. Groups, correct. Deepika Sharma, man, thank, correct. Groups we will be getting. So we will be getting the end of the day, whatever data provided, we get a groups, or you can call them as a regions. We get the different regions out of that, right? This is my job. Okay, correct, sir. Bharti ma'am, correct. Yeah. Nirmala ma'am also correct. So group of similar objects based on the shape, size, similarity, and the distances, we'll try to find out. And when I say classification, guys, correct, awesome. Identification of target belonging to a particular group, correct, awesome. Venugopal sir, your explanation is too technical, correct. So classification, when I talk about classification, guys, so I get a number of classes. Okay? I get a classes, categories. Guys, try to understand. We'll try to understand what exactly happening in classification when I'm starting with this logistic regression today. So prior to that, when I spoke about the regression task, guys, so try to always remember in regression, I am always predicting some kind of a number. End result is number. I get number of stocks, sales, number of days I will be getting the inventory, all any kind of a number if we are trying to predict here. So let it be stock price, let it be budget, let it be number, let it be money, let it be discrete, let it be continuous, float, integer, long, double, all category of numbers. Okay, so we are in, or let it be time series number, so it is still a regression task, guys. Okay, this is what we were able to understand. And then out of that, we were able to understand that first algorithm we started is the linear regression. We saw this also. What is and we saw a complete end-to-end roadmap, how the things gonna look like. And this is what we were discussing yesterday. Let me start quickly and tell you, guys, what we were able to discuss yesterday. So when I spoke about the linear regression, or when I spoke about the regression, guys, I told you that there are multiple algorithms available. So this is linear regression, or which can be also popularly called as multiple linear regression. Multiple linear regression. Okay. So let me write it in shortcut. Then ridge regression, then lasso regression, then polynomial regression. Okay. So this is what are the four popular algorithms for regression. And apart from that, the other algorithms are there which are versatile, which can be used for classification and which can be used for regression. I will not touch upon them as of now. Let's try to understand this one. And then I'll tell you like how the other algorithms can also do a job of the regression. So we were able to understand the regression task and what do you mean by regression. And let's imagine that whenever we trying to plot, this is the diagram, right? So this is the diagram we were able to understand. And when I am trying to plot, okay, my data and x-axis, this is x-axis. I was talking about the height. This example that I wanted to predict the BMI. So BMI becomes my target y, okay. And then I had an equation like this one, y equal to mx plus c. So this is the simple equation. You guys already told me this is the slope intercept format. And this equation when we spoke about, and let's imagine on x-axis I am taking height out here, height ht, and here I am trying to predict a BMI, right? So when I'm trying to fit a model, whenever I'm trying to predict something, so what is regression? Okay, what is regression? We spoke about we trying to predict a dependent variable based on the independent variable, independent variable in such a way that my main aim is to find the best fit line. Okay. So what is this base fit line? We saw also yesterday. I will again explain what is this base fit line. And my entire objective of the regression is to reduce or minimize, guys. Minimize the least square method, LCM. And least square method is something called as this one, yi minus y hat. Let me write it. Yi minus y hat. So what is yi? Yi is my actual point, and y hat is called as my prediction. Okay. And then this is something called as loss. So this is for 1 point, right? 1 point I was talking about. And then when I'm trying to make the sum of this, okay. So let me write it in better way. So when I'm trying to do a sum, guys, okay. So when I'm trying to do a sum, okay. So okay. Just a minute. Okay. So when I'm trying to do a sum, guys, so I'm trying to do a sum because in my data points, whatever data sets I had, all right, whatever data set I had, in data set, there will be n number of points, not a single point. So this is, I spoke about one single point. I was speaking about one single point. And when I speak about the entire data set, guys, my equation will change like this one. I'm going to take a summation for all the points because loss is for single point. That's what I said. Loss is for single point. When I'm trying to calculate the loss for entire data set, I'm going to sum the losses for all the individual points. That is I equal to 1 to n. 1 to n for all the data points. And like I told you guys, so whenever we try to create a loss and we try to sum the loss, some losses will be in the negative scale, some losses will be positive scale. And if we try to sum everyone positive, negative, there will be a situation that your entire sum will be get nullified. It will become 0. To avoid that situation, I'm squaring them. Right? And when I'm doing this kind of a loss calculation for entire data set, it is called as my cost function. It is called as my cost function. Okay. So this is called as cost now. So try to understand. And my entire goal is to reduce this kind of a equation. This is called as least square method. Least square method, because this square I want a least. This square I want least. Okay, this is my objective. And second objective, I told you to find out the best fit line. Okay. So this is what the regression is all about. So let me rub this thing and tell you. Let me tell you that how to find out the best fit line. Let's imagine, so say example, we are taking the BMI. I plotted the data here. I am taking a 2D graph out of here, and here I am, let's say I am taking the height out here. And when I put in, this is what my data looks like. And before that, guys, I told you that we have to check one kind of a relationship. So there is a relationship check we are doing actually before we start proceeding for the relationship checking. Actually, not one relationship. Actually, there are two relationships which you have to take. But right now, once I explain this model, I am going to explain, or before we explain this model, let me explain you the entire life cycle, data science life cycle, or entire life cycle of the modeling. So we can come back. But before that, I will tell you that whenever we try to fit a model, we have to check the relationship. And that relationship, I told you that we have to use the measure of the correlation matrix, or correlation coefficient, you can say correlation coefficient, which is denoted by this one, which has a equation like this one, xi minus x bar into yi minus y bar, okay, divided by standard deviation of x into standard deviation of y, or same thing I can call it as covariance of x and y divided by standard deviation x into standard deviation of y. So this is kind of equation. This is one type of relationship which we are trying to check, because my equation was this way. Simple linear equation, y equal to mx plus c. Here I am talking about only one variable, one independent variable. That's why I'm checking a relationship of y with the x. If x and y are related, then only it makes sense to put in this formula and try to find out the value of y, because value of y is dependent on x. If x is nowhere related to y, I should not taking that x as 2 in order to predict the y. That is the entire intuition, and that is the entire background out here. But when I am talking about the multiple linear regression, the simple change which is going to happen out here is, instead of one x, I will be having multiple x. So let's take the same example. If I have this kind of a situation where I am trying to predict my BMI, so BMI become my. So let me introduce some key terms as well out here. So when we trying to build our model, so in modeling, guys, we always talk about the target. We always talk about the target. So target is denoted by this one. So if I'm trying to predict BMI target, and it is called as always y. In terms of my codes, in terms of the jargon of the data science, it is called as y. And then based on the independent, so this is the dependent variable, right? And based on the independent variable, I'm trying to predict the things. So let's imagine that you have a age column, you have a age, you have a height, okay, you have a weight, and then you have a something called a gender. So here, everyone, I can call this as x1, call this as x2, x3, and x4, right? This is what I can call. So instead of one x, I have a multiple x. So my situation will be like this one. And when I'm talking about this x, guys, all these x are called as my features. This is something called as my features, okay? Features. And these all are denoted by x. All are denoted by x, and my target is denoted by y. Okay. So when and this situation or this equation will be like this, when I can write this equation as this way: m1 x1 plus m2 x2 plus m3 x3 plus m3 x3 plus m4 x4, and so on. Whatever variables, whatever n number of variable you will have, so on, and plus c. So this is what the equation change will happen. And then instead of one individual variable, one independent variable, I will have a multiple variables, and my y dependent variable will be depend on multiple variables. Guys, this is called as multiple linear regression. Now, in this case, when I have a multiple linear regression, then why I am trying to showcase you this equation before we try to plot our graph, before we try to plot our build our model, what I have to do? I have to check the relationship, guys, first. So I have to check the relationship. And that is why to quantify the relationship between the two variables, we have a measure something, one measure. That measure is called as correlationship. So what I am trying to check, I have to check the two types of relationship, type of a relationship. Before I build my model, guys, I have to check the relationship. One relationship I have to check is between, okay, between the features, and between the target, guys, between the target. Okay, so that means the relationship between all my x, here x stands for all my x1, x2, x3, x4, and xn. Okay, and my y target. Okay, this is what the relationship I have to find out. This is the first relationship I have to check. Why I'm checking? Because if there is no relationship, then there is no use of taking this kind of a variable. Let's imagine that you are plotted. These are the graphs. Okay, let's imagine these are the graphs, and here is the age, here is the height, here is the weight, and here is the gender. And on x-axis, this kind of variables are there. Obviously, on y-axis, I will be having a BMI everywhere. Okay, I have to check the relationship. If there is a no relationship exists, if the relationship exists, then okay. Age having relationship with BMI. Okay, very good. So this kind of a relationship is there with height and BMI. Oh, it's very good. Then I have a positive. Either I should have a positive relationship, or I can have a negative relationship also. So BMI decreases as the weight increases. So that is also good for me. But let's imagine this gender and the BMI. If it's not showing any relationship, this kind of a graph is there. So zero correlation. At that time, guys, I don't have to take gender in my equation of this linear regression, which equation I was talking about. Okay. So this kind of a relationship I have to check between the feature and the target. If the relationship checked, and after that I found out that only age, height, and weight are related to BMI, then gender is nowhere related, then I have to drop this column. I don't have to take, because it's not making any sense for me to take this equation. So my equation should become this way: y equal to then mx1 plus m1x1 plus m2x2 plus m3x3. And then this gender will not be taken, which was x4, right? So this is what I have to do. That is why first thing what I do is I try to check the relationship. So if I check a relationship, there is a relationship between the feature and target, then only I should proceed by taking that kind of a features. Otherwise, this thing, guys, this thing is called as feature selection. And there is an entire topic, there's an entire book that how can we do a feature selection. So this is very important to do a feature selections. So once I do a feature selection only, then only I can go ahead and build my model. Okay, build my model. Second thing, now this relationship we understood. This is the first relationship we're trying to talk about. Now let me rub this thing. So second relationship, what I have to check. So second relationship, guys, I have to check is, and that concept is called as multicollinearity. So multicollinearity. Okay, this is the concept it is called as. Now, what is multicollinearity, and try to understand what kind of a relationship we are trying to find out. So here we are trying to find out the relationship, guys. Here we are trying to find out the relationship between, or you can say among the features. Among the features. So what do you mean by relationship among the feature? Let's take the same example. What I'm going to do here. So if I have an age, if I have a height, okay, if I have a height, then I have a weight, and then I have a gender, guys. So what I am going to do is I'm going to find out the relationship of age with the height, with the weight, with the gender. Then similarly, I'm going to check the relationship of height with the age, with the weight, with the gender. And similarly, I will check the relationship of age with the weight, height, and gender, guys. So this kind of a plot I'm going to create. So I will be checking. So what is the relationship of age with the height, with the weight, and with the gender, guys? So why I'm doing this? Why I'm doing this? And this concept is called as multicollinearity. Multicollinearity, guys. Try to understand. So why we are trying to do this and what is the main purpose? Why we are trying to find out this kind of relationship? Every variable will be checked with each another to find out is there any relationship exist. Why we are trying to do this? Because guys, what this says, the rule says, what the rule says, if there exist, if there exist, if there exists the correlation, if there exists the correlationship among the variables, guys, among the variable, among the features or variable. So we have to do, what we have to do is, all of them are not required. All of them are not required for the prediction. All of them not required for the prediction purpose. This is what the rule is. So what I have to do then? If there is a correlationship exists, then what I have to do? Simple thing, what I have to do is, whenever there is a relationship exists, let's imagine the relationship exists between the age and the height. Okay, so you have to draw, you can do two things, 2 to 3 things. Either you drop one of them, or you can do one thing, you can try to merge them together and try to create a new feature. So this is what the rule says. Okay, this is what the rule says. This is what the thumb rule is there. So whenever there is a relationship exists, that relationship is called as multicollinearity. Multicollinearity, guys. Multicollinearity. You have to do a multicollinearity check before you start to build a model. So multicollinearity check is among the variables, among the features. Which features are correlated to each other? If the features are correlated, then you either drop one of them, not all of them, one of them. Or why? Because try to understand this way. This I will tell you the example also why they are not taking all of them and why they are dropping one of them, or why they want to merge the features together and try to create a new feature out of them. Let's imagine this way. Now, whatever example I give you, there are only 4 to 5 features. 4 to 5 features in real time. Whenever I worked with the algorithm, whenever I try to perform the modeling, guys, at that time we had around 100 to 200 features. 100 to 200 features were there. And try to understand whenever I try to create a relationship graph, between the target and between the features. So how many graphs I have to create? How many graphs, guys? Let's imagine there will be always one target group and one target group with the all 200 other features. So imagine what kind of can anyone tell me how many graphs I have to create to find out the relationships, such relationships? Okay, any number, very close number, if you can do, not exact number. How many such 2D graphs I have to create? Because my human mind can understand only 2D and 3D pictures. Beyond that, the human mind cannot perceive the things. So if I want to find out the relationship, obviously I have to do a XY coordinates, and this kind of a plots I have to create, right? So whether there is a relationship this way, or there is no relationship. So then if I am saying that I have to create a relationship graph, obviously the method to find out this multicollinearity, I will tell you the method. So method is to find out by using this kind of a visualization. Okay. So how many graphs exactly I will have to create, guys, to find out is there any relationship between target and feature. So let's imagine I have a 200 features and one target column. One target and 200 feature. How many graphs, such 2D graphs I will have to create? Can anyone tell me? How many graphs I have to create here? Yeah, guys, quickly. So one is to one, like 2D graph I have to create, and 200 features are there. So approximate number, if you can give me, how many graphs I will have to create to find out the relationship? Anyone? Any clue? How many such permutation combination I will have to do? What will be the number? Any close number, if you can give me, that will be sufficient, guys. Common. Okay, let's understand. Based on the target. Yeah, guys. Based on the target. One target as Y, and then X-axis, you will take one variable at a time. Such how many graphs you have to create if you have a 200 variables, 200 features. Such how many graphs you have to create. That's what I am saying. 100? No, more than 100, because I have a 200 features. No, more than that. 200 graphs. No, 200 graphs will be like for at least minimum 200. Okay. But there will be more combination. Okay. 200 graph for first target and feature. Okay. Target and feature. 200 graph. Then try to understand second graph which I have to create is between the features. Like 200. Yes, 200 factorial. Correct. So 200 factorial. Yes, ma'am. Priya ma'am, correct. Anjali ma'am, correct. So 200 factorial graphs you have to create, and imagine what will be the huge number, right? Huge number. So that is why there is a concept. That is why there is a concept called as dimensionality reduction. Dimension reduction. Okay. So coming back to this one, why I am trying to find out the multicollinearity. That is the main reason, guys. If you have a multiple features at that time, if you have a 200 feature, obviously all of these 200 feature are not contributing. All of them are not contributing to the decision making, towards the prediction. So that is my main aim. That's why I'm trying to find out the multicollinearity concept, guys. And to find out the multicollinearity, guys, there are two methods. Let me tell you. One is called as VIF score. One is called as VIF score. And other thing I already told you, correlation coefficient. Correlation coefficient. So what you have to do is you have to plot a correlation graph. So this is data frame dot CORR graph. And once you create a graph, guys, you'll get this kind of a correlation where diagonally it will be diagonally one. And then guys, there will be something like that, BMI, and then there will be age, then there will be height, there will be weight, and there will be gender. And similarly here also. So here also, like say, let's say this way, BMI, then height, then the weight, then the gender, and this kind of a correlation numbers will be there. 0.8, 0.6, 0.2, 0.5 minus correlation chip. Okay. So this kind of a graph will be, I will show you this graph, guys. I will show you this graph. And this is called as correlation plot. Okay, correlation plot, which will show you the correlation number between this one. Okay, within one plot, within one table, one matrix, it will have all the correlation value. So this is the one way. And whenever you find the correlation is more than 0.6, so these are the there exists a multicollinearity. Okay, this is the one method. Correlation coefficient value you are trying to plot here. That's correlation coefficient matrix you can create. Second method, what I talked about. Second method is, guys, we talked about is VIF. Now try to understand what is this VIF formula. Okay, so what is this VIF? VIF is, guys, variance inflation factor. Variance inflation factor. Okay, variance inflation factor. This is what called as VIF. And what I have to do is simply I have to create this kind of a things. So this is automated. This is automatic function, guys. This is available, implemented. You just have to call this function and it will try to give you this kind of result. So it will show you the VIF score and the column names. Let's imagine this way: age, height, weight, and the gender. Okay, gender here, and there will be VIF score. And now rule. What is the rule? If the VIF score is between 0 to 5, then that means there is a no severe multicollinearity exists. No severe multicollinearity exists. If the score is greater than 5, then we have a problem. If the score is greater than 5, guys, there is a multicollinearity exists. There exists the multicollinearity. We have to drop that column. So let's imagine this way. So age is showing like this way, 5. Height is showing 3. This is showing 4, and this is showing 6, guys. This gender. Now, guys, look at the score. Now, you obviously what you will try to understand. If the score is between 0 to 5, so for age it is 5, it's okay. For height, it is obviously low. For weight, it is obviously low. But for gender, guys, so gender, you can see the score is 6, means there is a multicollinearity. So this kind of a table you will be able to get. You will be able to plot a table directly using the VIF function. VIF function is available in the sklearn library. So you plot this one, and then you can choose the variable. So now you can choose age, you can choose height, you can choose weight, but you cannot go with the gender. You have to drop the gender because there is a multicollinearity. So these are the two ways, guys. These are the two ways how you are doing a feature selection. Then once you are able to do this feature selection, then you guys, what will happen? Then your model will come here. Then it will try to plot this way, this kind of a graphs. And this I am showing 2D, but in fact, there will be like 3D graph or 4D graph as per your features. And then it will try to plot the data like this way. Y will be target, X will be your features. And then once we put this, guys, once we put what I told you, my main aim is to find out the best fit line. So best fit line is the line which goes through the maximum data point. And the equation of this line will be Y equal to MX plus C. So I am trying to showcase this is a 2D, but when in reality there will be multiple X and multiple Y. Okay. So this is what happens. Now try to understand. Now coming to the real scenario. So how I am able to fit this kind of a line, and what is the main aim, like how I'm trying to do this kind of a things. Okay, and what is my predictions then? So whatever points, let's take this point now. Okay, so what I have to do is, guys, so let's imagine. So this distance is called as residuals. This distance between the actual point, this black point is actual point and red line is my regression line. So this is called as my regression line, guys. Regression fit line. So this distance, this difference is called as residuals, or it is called as error. It is called as error, guys. Okay. So try to understand this one. Why we are calling this error and why we are trying to say this kind of a things. Okay. So let's understand this one. So what we trying to do and what is our main aim and why it is called as error and how to identify the errors, guys. How to identify the errors. Let's understand this way. So when I'm trying to talk now, we'll speak about the errors and what are our prediction actually. What is my predictions? So whatever the points, guys. Okay. So whatever points are there on this red line, if this is the point for which I am trying to do a prediction, obviously I will find a corresponding line, corresponding regression line point for that point. So let's imagine this is the point, corresponding point on the regression equation. So this become my prediction. This become my prediction for this black point, guys. Okay. So this is how for each and every point, this red line will become a prediction point, and this is what is called as y hat. Y hat. Now try to understand. I'll try to show you something and some important concept, guys. Okay. So this is called as a error. Now we'll try to understand how what type of errors are there and how to find out. Like best fit line says that whatever these differences are there from the actual point, some differences are positive, some differences are negative, right? This way. So this difference should be minimum. So whatever the points I'm showing and what is the connection, these vertical lines I'm showing, this distance should be minimum. Maximum, we try to minimize this difference. And this is my main aim, guys. This is my main aim. This is what I'm trying to understand. And this is what I'm trying to say, that this is what should be the prediction. And this is what it should look like. Okay. Just give me one moment, guys. Okay. So when I'm saying this kind of a prediction, when we speaking about this kind of a thing, now I have to understand the types of error, guys. Or before even I go, guys, into this kind of a things, so let me tell you like what happened. Okay, let's do this way. First, I will explain you this, what is the type of error, what is R score, and then I will try to understand or make you guys understand that whenever we are building the model, what are the step 1, step 2, step 3 we are doing, and how we are trying to build the model. Let's understand the regression model first. Let's understand the regression model first, and we'll try to understand the entire life cycle actually, and then we'll make a code walkthrough that will make a sense, guys. Then that will make a sense that how the actual model is built and what are the steps. Now let's understand the working. So we are able to understand that this is called as error. This is called as my prediction. Yellow point is prediction. YI is actually actual point. And what I have to do is I have to calculate. Once I fit, guys, then once I did a prediction, I got a Y hat actually. Y hat. And my loss will be actually this way. My loss will be actual point minus my prediction point. This is become what loss. And this is for one point, and I have to minimize. This is what I said, right? For all the points, because this is was the single point actually I was talking about, right? Now I think graphically it is become very clear why I'm talking about the single point, why it is called as the single point equation. So because I took one black point and tried to find out the prediction which is lying on my red color line, which is the regression line, and then that difference I am trying to find out, that difference is called as residual or error, the error between the actual and the predicted one, right? So when I'm trying to perform this calculation for the entire all the data one, that's why I'm saying by I equal to 1 to n, guys, 1 to n, whatever n number points are there. Then I'm squaring them because to nullify, because some differences are down, are negative, some differences are positive. So just to remove that nullification effect, I'm trying to square them. And then this equation is called as cost. This equation is called as my cost function. So this is called as my cost function for the regression equation, for the linear regression. Okay. So try to understand. This is what is going to happen. Now let's try to understand what is happening. So whenever, guys, whenever I don't have a regression equation like this one. So but still people were doing before regression also, people were doing this kind of a prediction. But this prediction, let's imagine this prediction was, let's call this as the average line. Average line Y hat. Okay. Let's call this as a Y hat. Okay. Y hat. And let me rub few things so it will not be difficult for you guys to understand. And let's do again the things. Let me again create this one so you guys will be able to understand what we are speaking about. Okay. This is XY. And let me do the prediction line as well again. So this was my prediction line actually. and this was the equation, and then we have a points out here also. Okay. So this was what we were speaking about. Now try to understand, guys. Before I go ahead and tell you something about the types of errors, actually how to calculate error. And once we calculate the error, guys, then we'll try to understand how my regression equation, whatever the regression model I have fitted, whether it is performing good or bad. That kind of a decision, performance evaluation, I will try to do. For that purpose, guys, let's understand the errors, right? And how to analyze the errors. And once we analyze the error, I have a certain kind of a parameter, some kind of a evaluation parameter. How I can evaluate my model is good model or better model or best model, or is the worst model, whichever I am trying to fit out. And once we understand this working, guys, then we'll try to understand what is called as regularization. What do you mean by polynomial regression? Why we require polynomial regression? Why we require lasso regression? What is the use of this kind of a regression equation? And that's all. And then we'll try to focus also on the code walkthrough, logistic regression. And if time permits today itself, we try to cover the algorithm, which is called as gradient descent. Very, very beautiful algorithm, very nice algorithm. And this is the algorithm which is responsible to find out the value of MNC. Everyone is very, very interested and keen to know how we find the value of MNC rate. So I will explain you exactly how the algorithm runs in the background, how what kind of a mathematical collection it does, and how it is trying to find out the optimal value of MNC so that it is able to perform the prediction correctly. So this is what we're going to understand now. So let's quickly try to understand what is happening here. So guys, whenever there is a data, and whenever I didn't have this concept called as linear regression, because using the linear regression, I'm trying to do a prediction of the numbers. Okay. So can you guys like tell me, like before regression equation, whenever I am trying to do a prediction of the sales, very simple example, sales prediction I am trying to do. Let's imagine this is Diwali season. This is the month of November 23. And someone wanted to make a preparation, any business want to make a preparation for this Diwali. And what should be the stock I should keep? What should the prices I should be able to keep the products? And how many products should I keep, right? For that purpose, they will try to predict what will be the my sales, right? What will be my sales in during this Diwali season. This is a very important month and this Diwali season. What should be my sales? And according to the sales, somewhere in the month of October only, in the month of October 23 only, they will make a prediction. And according to the prediction, they will start working towards the Diwali. So they want to maximize their profit, guys. So can you guys tell me, whenever I don't have kind of a linear regression equation, which I am trying to fit here, so how you usually people used to do a product prediction for do a forecasting for the sales, guys? Can anyone tell me what was the formula or what is the measure they were using to forecast what is the sales for upcoming months? So can you guys like tell me basic stats formulas, how using what formula I will be able to predict what is going to be my sales upcoming month or upcoming year or whatever things I am trying to predict. Can you guys like tell me what is the basic formula used for the prediction? Okay. So if I want to predict sales, so if I don't have this regression equation with me, so how I should do a prediction? Can you guys tell me? Anyone? What is the measure used for the prediction, guys? Very, very simple stats measure is used. If you could remember our classes for stats classes, 11, 12 classes, where we used to have this kind of equation. Please predict the sales for this number, right? Number, this month, what will be the sales for this business, right? And we used to solve this problem. Base value for plus growth, correct? Number of leads into conversions. Awesome, awesome. These are marketing concept, but a statistical concept actually I'm looking for. Base value for growth, correct? That is a correction, like you are trying to keep a margin. Base value plus margin, that's what sales you are trying to understand. But any statistical measure we used to use? Anyone? Very, very simple. Answer is very simple. You will laugh like what I am talking about. Any simple measure, statistical measure. I'm giving you a hint that what is the statistical measure we are using to predict the future when looking at the past data. Yes, awesome, awesome. That's what I was looking for, Priya ma'am. So average, correct. Hemant sir, correct. So means of previous year, correct. So when we did not have this regression, or when we are not doing any kind of a calculation, simply what people used to do is people used to create a kind of a average line. So this is what average line I'm trying to predict, guys. This is very important to understand, because whenever we trying to understand my errors, correct. Awesome, guys. So let's imagine this is my average line. Okay, this black line is my average line. Oh, awesome, awesome, guys. Number of units sold per units. Correct, awesome. This is what we're doing. And but most probably what people correct, ma'am, Nirmala, ma'am, Dr. Nirmala, correct. So what people used to do is, guys, try to understand this way. So whenever they did not have any other measure, simply what they used to do is they used to calculate something. Let me rub few things out here. Correct. Maximum average sales, guys. Correct, correct. Average sales to perform the prediction. Okay. Let me rub these things now and let me tell you like what people used to do. And in average calculation also, guys, in average calculation also, they had a different methods. Like let me understand and let me tell you. So whatever average they are calculating, either they are calculating simply average for the last 3 months. Last 3 months average I will be taking. I am saying that the fourth month this is going to be a sales. No, or what people used to do is they had a concept. Okay. Precision recall measure. Yeah, that will come into the classification, ma'am. Actually, Bharti ma'am. Recall precision will come into the classification algorithm. Here, and we are trying to understand the regression algorithm. Here, it will not come into picture. Okay. So here there is something called as R square. This is R square, mean square error. This kind of a measures will come. So we'll try to understand this one now. So guys, first we are trying to understand what type of errors are there actually. What type of errors? So for that purpose, we understood that whenever I did not have a regression equation, I used to do a simple average, guys. Simple average. So average could be last 3 months average, or if someone want to be very precise, they used to do a cyclic averages, cyclic average or seasonal average, guys, seasonal average. So cyclic average means I will be taking last 3 months average, last 6 months average, last 4 months average, or I can do a like for like. Very famous concept in the business is like for like. Like for like means what? So if I'm trying to predict my sales during the summers, sales for the summers. So usually in India, summers is, guys, between somewhere between the March and to till the May, March and May. So if I'm trying to find out in March and May in 23, year 23, what's going to be my sale? Obviously, what I have to do is I have to take the value of the March to May 2022. Okay. And but last year, like for like, last year, same summers, what was my sales? It's more likely to be the same sales during my next year. Okay. This is what people used to do. So rather than taking last 3 months, because in last 3 months could be the Diwali season. So where Diwali could be more, or you say winter season. In winter, the summer items like ice creams, or could be the umbrellas, or could be the water bottles, could be the breezer, chillers, or that kind of a stuff, right? Will not be sold. So that's why people used to go for like, LFL concept, like for like concept. And whenever I'm trying to do a seasonal or cyclic pattern, what is my seasonality? Compare the same year seasonality with the last year seasonality and try to compare, guys. So that is why in regression also, they're trying to find out what is my average line. And whenever people don't have this regression equation, they used to have this kind of a average line equation. And based on the average line, guys, based on the average line, they used to do prediction. Now, what is happening when I'm trying to fit my regression equation? I am trying to lift my error. So imagine, so actual error. There is something called as, now let me rub few things and let me start writing few things now. Actually, so let me rub this entire mess and let me start understanding and let me start writing the actual things. What I was to speak about, guys. The errors are something called as total sum of square error total. This is total error. So sum of squared error, SSE, something called as SSE, and something called as sum of squared error regression. So these are actually 3 types of error which I have to find out, and how to find out this error, try to understand now this way. Okay. So whenever I have guys, whenever I am trying to fit this kind of a regression equation, this kind of a gap I am trying to fill, right? This kind of a gap, this distance is actually covered by my regression line. Try to understand. So what is my total error? Total error is called as sum of square error total. So total, this is called as total error. The total error is this one, guys. This. So actual point, yi, and y bar. Y bar means average. Y bar means average. So the difference between average and the actual point is called my total error, SST. Sum of square total. So I am saying total error, guys. This error, this portion I am talking about now. Okay, this portion is called as SST. SST, guys. SST. Okay. So let's try to draw here also. I am trying to draw this one. This is my regression point. And same thing I am trying to draw here as well. So this is my average point, y bar. So this will not be a mess. You guys will be able to understand. This is my actual y equal to mx plus c, right? Regression equation. And then this is my actual point here. So what difference I am trying to find out here is, so whatever the difference between the actual point and this this average line is called as SST, guys. SST. Okay, sum of square total. Now try to understand. Then I have a average y hat only. And that after introduction of the regression line, what the total error percentage was reduced by the regression equation. So this red line difference and the black line difference, this difference, guys, this has been reduced by my regression equation. So that is why it is called as SSR, sum of square error due to regression, sum of squared error due to regression. So let me call this one also here SSR, sum of squared error due to regression, because due to regression line, this out of this portion. Okay, let me draw this portion with a different color now. So maybe this one color is better. So this much portion, the green, which one I am showing indication using the green one, green color. So this much portion of the error actually reduced by my regression equation, guys. So that is why it is called as SSR type of error, SSR. So let me write the formula for SSR now. SSR means it is the difference of y hat minus y bar, average and the prediction difference. Now guys, SSC, last thing, that is going to be a irreducible error, and let me write that error here. So actual and the prediction. So they same thing, actual minus predicted. Actual minus predicted. What we lost, we calculate. So this is called as SSE. SSE, sum of squared error. Sum of squared error. And this error is irreducible error, IR. This error is irreducible. We cannot reduce this error, because even though I can go close to this point, actual point, but I cannot have an exact point. Why I cannot have exact point, guys? Because let's imagine this way. If I try to have, if I am having this kind of a equation, this kind of a plot is there. This is 0, this is x, this is y, and this is what I am having. If I am trying to fit each and every point, let's imagine, if I am trying to find out the difference between the actual point and the prediction point is 0, means what is happening, whatever the actual point is there, that same actual point I'm giving you as a prediction. That is what happening. For that purpose, what I have to do is, if this is my data set, I have to fit this kind of equation which is going through each and every line. So each and every point, actually this line has to go to each and every point. So then only it is possible that my yi means actual point and the prediction point will be difference 0. So this cannot be 0, but what it can be approximately 0. Approximately 0 means near to 0. And this is my main goal also. This is my goal of the regression equation also. Okay. So everyone understood this difference I am calling now SSG, guys. SSE. So SSR, SSE and SST, guys. What is happening is, whatever the total error was there, which was because of the average I was using, and then I fitted a red color equation line. This is the regression equation, and this regression equation was able to reduce my error. So that is called as SSR, and then SSE is my actual point minus prediction line. So this kind of errors are there. Now everyone understood what is total error, what is SSE, sum of square error, and this is called as irreducible error, because this cannot be reduced. Irreducible error, guys. Okay, so this is called as irreducible error. This cannot be removed, because if this is removed, that means I am getting 0. This difference is 0, means whatever the actual point is there, that same actual point I'm passing as a prediction, and this kind of a equation is getting fitted here. So this line, and which is not a straight line, which is not a equation y equal to mx plus c. Y equal to mx plus c equation will be always having a straight line. Always having a straight line. Here, this is not a straight line, this is a curved line. All right, guys, cool. Everyone understood what is SSC, irreducible error, what is SSR, what is SST, and that is why my main aim to reduce this SSC means this red line goes near to this actual point, black point, in such a way I have to fit a base fit line, and this is what the entire concept is all about, and this is what the entire regression works upon. Okay, and this kind of a 3 errors. Why I am telling you these errors? Because let me rub this. Okay, why I am telling this error? Please tell SST once. Okay, okay, guys, I will tell you SST. Let's draw this one here on the second diagram out here. This diagram number 2, try to focus here, and I try to calculate actually SST. So try to understand, this is my actual point, and this black line. Okay, so black line, I try to showcase this black line with the red color. So this red color line, okay, let's imagine this red color line is my regression line. Okay, guys, this red color line is my regression line, and try to understand, this is my actual point, and this is my regression equation I have fitted. Now try to understand, before the regression I had an average line. So somewhere middle will be average here. So let me draw the average line here. So that average line will be called as y bar. Okay, y bar, guys. Try to focus please again on the graph number 2, and where I will explain again all the things. Now try to understand. Let me draw the prediction line with the yellow color now. So on this red graph, if I want to do a prediction, and obviously the equation of this line will be y equal to mx plus c. Mx plus c, okay? Mx plus c, this is my regression line. Okay, this is my regression line. So try to understand why for this regression equation. what is this actual point is there. For actual point, if I try to do a prediction, what I told you, we try to plot the data first. We try to create a regression line, which is passes through the maximum data point. And my goal is to reduce the loss. My goal is to reduce the loss function versus actual minus predicted difference. This difference has to be minimum. This is called as sum of least square method. Least square method, LSM. Least square method means yi minus y hat actual square. This has to be minimum. This is my cost has to be minimum. My loss has to be minimum, right? So always try to reduce the loss. This is my main aim. But try to understand, I cannot exactly have a zero value. If I'm trying to create a zero kind of equation, my actual and the prediction zero, not possible. Try to understand in stats also we have learned that whenever I am trying to estimate the population parameter, based on the sample parameter, I can go near to that. I cannot create a entire exact prediction. So that is why we have something called as confidence interval. So let me write that confidence as same formula, same equation is applied over here also. So what I try to do, whenever I try to based on the sample, this sample mean, I'm trying to pre-populate the estimation of this population mean. So I write something like this one. X bar is my population sample mean. X bar plus minus sigma or S. Sigma or S, not sigma or S, or we can write this as a. So let's write first the standard score. So X bar plus minus T or Z score, right? We use T or Z score. Then sigma by root n. Sigma by root n is my error. So what I say is that whenever I try to populate, I try to write this kind of equation. This is called as my confidence interval, because whatever sample population mean is there, I can try to estimate that population mean based on the sample mean. Sample mean is X bar. It can fall into some range. So it can be between somewhere plus or minus range. If this is my mean, this is the mean of the sample, my population mean can fall in the range plus or minus. It cannot be exactly, I cannot go exact, right? This is my stats formula. That is why we have something called as confidence interval. So this is what the formula I write based on the sample Z or T score I use. So that is why same equation, same situation is out here. You cannot exactly predict the value. Without God, no one can predict the exact value. But we can go to nearby, very, very near to actual value, but we cannot exactly predict. If you are predicting, means your model is overfitting, your model is wrong. If you are predicting 100% accuracy score, your model is totally wrong. Your model is wrong. So that is what we're trying to understand. So when I'm trying to take, now come back to our equation 2. Now you got the situation background, why they are doing this way. So try to understand, whenever we have this kind of equation, graph number 2, at that time, whatever the difference between the average line and the prediction line, that is called, that difference is called as SSR. Because of the regression, my error is reduced. Actually, what is my total error? SST is called as my total error. So total error is this, guys, difference between the Y bar and the actual point. This Y bar and actual point is this difference is called as sum of square error total. So this is called as total error, guys. Okay, guys. Okay. So I will pass on this message to my colleague to add this number. Okay. So guys, this is called as SST, and my total error is reduced because of the regression equation. So that much portion has been reduced. That is why it is called as SSR. And I cannot go exactly near to the exact point, but I can have some error. So that is called as SSE, guys. Cool. Everyone understood now what is SSR, what is SST, what is SSR, what is SST, and what is SSE, irreducible error, guys. So this is what the errors are there. And my main goal is, guys, to reduce the loss function. Okay. So guys, let me rub this thing now. Everyone understood. And when I wrote about this SST, SSR, why I'm writing this? Because so I have something called as performance evaluation. So performance evaluation of my regression model. Okay. So whenever I'm trying to fit the equation, guys, whenever I try to fit a model, I have to evaluate my model, whether it is a bad model or good model. So the first evaluation, what I have to do is, there are various, now I don't want to waste much time, guys, on regression, because we have to start our logistic regression. We are still yet to discuss reach Lasso polynomials. So try to understand this one very quickly. So what do you mean by the performance evaluation? Performance evaluation characterize, you do a residual analysis now. Residual means error, residual analysis. So I will show you what is residual analysis. So you can do residual analysis. I will show you what is residual analysis. And then you can do something called as R square. And then you can calculate something called as mean squared error. Mean square error. Okay, so something called as mean square error. And then guys, there is a fourth formula which is called as adjusted R square. Adjusted R square. So this kind of a formula is there. So let's understand first R square, MSC, and R adjusted R square, and then we'll come back to this residual analysis. What is this residual? Very simple concept is there. Residual adjusted R square. R square is the main formula, guys. Now try to understand what is the formula for R square. So we spoke about that errors SST, SSE, and SSR. Correct. So let me write this very fast, and let me draw this here also. So let's keep this one. This difference is called as SSE. So this is the average line. This difference is called as SSR. And this the total difference is called as this from actual point to Y bar line is called as SST here, right? So guys, when I say R score tells us how much error. This R score says how much error is been explained by my model. How much error or variation is been explained by my model. That is what the R score denotes. Okay, so the formula for R score is guys this way: SSR divided by SST. SSR by divided by SST means out of this error, whatever error has been out of total error, whatever error is been reduced by SSR, how much that as compared to the total error, that ratio we are trying to calculate. Or the same thing you can write this way also: 1 minus SSE, 1 minus SSE divided by SST. SSC divided by SST. This kind of a ratio we are trying to calculate. We are comparing whatever error has been reduced by regression with the total error, and this ratio we are trying to calculate. Maximum the ratio, better the model. Max the ratio, better the model. That is the equation here. So max the ratio. This ratio will be given between 0 to 1. So 0 to 1 value will be given by this ratio. So this SSR by SST or 1 minus SSE by SST, right? So SST I can write as this way: SSC plus SSR, correct? SSC plus SSR, and then you will understand why I'm writing 1 minus SSC by SST, right? And this SSR is like Y hat minus Y bar, and SSC is actual point minus the prediction. Okay, so this is what the equations are said. So R square we have to calculate first. First formula is R square. If your R score is high, that means max, the better your model is performing better, guys. Your model is performing better. Now try to understand. So why there is something called as adjusted R square. Adjusted R square. Now try to understand. Whenever we have a single model, or whenever we have number of features are less, like 5 or 10 features are there, at that time R score performs very good. R4 perform very good. It gives the actual picture of how much error has been reduced by regression. But whenever the your feature increases, your R score also tend to increase, guys. R score tend to increase. That's why we have something called as adjustment. We have to do some adjustment to the R score, and that is called as adjusted R score. And the adjusted R score formula is, guys, this way: 1 minus R square, 1 minus R square, n minus 1 divided by n minus p minus 1. Okay, so this is the formula for adjusted R score, guys. Try to remember. This is what you have to calculate. So what is this n? What is this p? I will explain you. This n means total number of data points. Total number of data points. P means predictor. Or you can simply say the features. And features mean number of columns you are using. Okay, and then R score, you already know what is this R score. So this formula, they are doing adjustment, because what is happening is your number of features are increasing, and increasing that feature, guys, causing the problem for R score. This R score get bulged. It is showing more. Actual picture is not given. So that is why we have to do some adjustment to the R score, and this is the adjustment: 1 minus R score, n minus 1, n minus p minus 1, guys. So this is called as now adjusted R score. We have to calculate adjusted R score when the number of features are more. Guys. So we have to check both R square and adjusted R square. And what is MSC then? What is MSC? Mean squared error. Simple, guys. MSC, mean squared error, is same thing. So it is like we are trying to take the mean square error. Okay, let me write this mean square error. SSE divided by, this is SSE for 1 point, right? So we have to calculate for all the point, n minus 1. So this mean error, we have try to take mean of the error. So that is called as mean squared error. We have to divide by number of data points. Okay, and there is something called as RMSE. RMSE, root mean square error. RMSE means you have to take the under root of this. Guys. This is called as RMSE. So these are the measures. Okay, residual analysis, R square, mean squared error, and adjusted R square. and you understood SST, SSE, SSR, and what is this looks like graphically you understood. So guys, before I proceed, everyone clear? Everyone okay with this concept? So last thing I will explain you graphically within 2 minutes, and we'll try to move to the ridge regression, lasso regression, guys. Okay. Okay, guys, thanks for the confirmation. Let me rub these things. So let me rub this thing. And last thing try to understand is residual analysis. Residual analysis, okay? Something called as residual analysis. Don't worry, guys. All these things will be written in the notes, and you will get this kind of a note. Don't worry about this equation and all. This is already there. So I'll provide you this one. Okay, residual analysis. So residual analysis means what? So residual analysis, I told you residual means errors. So what I have to do is whatever your errors are there, you have to plot this error this way. Okay. So you have to create a graph of your errors also. Let me show you the graph of the errors. And by using this graph, guys, you can explain that whatever graph you have created, whatever graphs you guys have created, by this graph, you can analyze whether your model is performing good or bad. Okay. So let's try to understand. So now this is something called as 0 point. So obviously my loss yi minus y hat. This I am trying to create or minimize the loss, and I am trying to make it near to 0. That's why I'm saying this approximate sign, not exact sign equal to sign, approximate to 0. Now let's imagine you took the errors, whatever errors you calculated for all the data points. Now you plotted these errors, and these errors are looking this way, guys. Okay, so this is your 0 point, and around the 0 they are spread like this way. Around the 0 they are spread. Okay, so this kind of a graph is created, and this is graph number 1. This is graph number 2, and this is graph number 3. So you have this kind of a graph which is created, and your errors are actually spread across. And we try, whenever I try to see above side and below sides, the errors are like constant. There is a constant variance among the errors, and they are trying to form this kind of a shape. This kind of a shape. So this kind of a shape, guys, is called as homoscedasticity. 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 City. Okay. Homoscedasticity. Homoscedasticity. This is very good. If your error are spread across the 0, and the difference between the errors are constant, because you can create this kind of a line, and this is kind of create a rectangle shape, means above the error, above differences, below differences constant, guys. Okay, so whenever you try to plot your error graph, and your error graph look like this is called as homoscedasticity, guys. Homoscedasticity concept, and that means that your error are spread across evenly above and below. Yours across even, they are even, right? So above the distance, below distance are even, guys. Even these distances are even, and they are in the same proportion. So this is called as homoscedasticity. Now try to understand, if your errors are looking like this way, where the differences are not spread across evenly, so they will try to form this kind of a shape, guys. This kind of a shape. And if you try to connect this graph, so the graph will show you this kind of a triangle actually. Means what? The difference out here is larger. The difference is small, and it's getting small. Okay, the difference is not constant. Non-constant variation. Non-constant variation. This is what is called as, and this concept is called as heteroscedasticity. Heteroscedasticity. City, guys. Heteroscedasticity, this is wrong actually. This is your wrong model. When you try to take the residuals, your errors, and you will try to plot them, if the graph 1 is shown means it is very good model, because your errors are spread across evenly. Even your errors are even, means your errors are like this way. So whatever prediction you guys are doing, this prediction are close to each other. So the difference between the between the prediction and difference between the errors are constant. They are falling in some range. Okay. And then let's imagine one, and I will explain you by giving numbers. So let's imagine you are trying to predict BMI, and your actual BMI is 30 actually. Your actual BMI is 30. So when you did a prediction first time, the first time it is showing you prediction as 35. Second time it is giving prediction 25. Third time it is giving prediction, let's imagine this way, 38. Second time it is giving 22, and third time 21. So try to look at the difference. The difference is 5, 8, 5, 2, right? So if I try to plot them, this is 30. So they are going this direction. One is going high, one is going low again, and one is going high, one is going in negative direction, right? So this is 30, some is going below, some is going above. So this graph is like very big. So this is wrong actually. The variance is very high. The difference between the actual and predicted, the distances are very high. And wherein if you try to look at this distance, these are close to each other. So this is a good model actually. This is good model. This is a bad model. This is a bad model. This is what we trying to showcase, guys. Here using the residual analysis means if I try to do a prediction and my actual prediction is 30, but my prediction are falling in this range, let's say 32, 31, 29, or let's say 28.5 means which are very close to this one, very close. Okay, if on the scale, it will be like this way only, very close to this one. So this kind of a model is very good, guys. So that is what we're trying to understand. And the third graph, which I was talking about, which was for the non-linear shape data, non-linear shape data. So let me show this with a different color now. So if I have a kind of a, this kind of a graph, guys. So, and if I try to plot this graph and then try to attach this graph, so it will show you this kind of a half circle this way, this spherical shape, half spherical shape. So this is for non-linear shape data. This is called as non-linear shape data, non-linear shape data, guys. And this is also wrong. This is also a heteroscedasticity, guys. And this is for non-linear data. These were for the linear data. These were for linear data. And then when you try to do this kind of residual analysis, guys, you will understand your model is not good, or whether it is good. Homoscedasticity good, heteroscedasticity not good. Okay, cool. So this is how entire algorithm works, guys. This is how the entire algorithm works on, and this is how we can analyze your algorithms, and this is how we can understand what is the regression equation goes on. Now you have understood this equation. Now this is called as multiple linear regression. Now try to understand. Now try to understand what do you mean by ridge regression, lasso regression, and what do you mean by polynomial regression. Let's take a very simple example. Let's take a very simple example. So if I am trying to predict, my use case is this way. I will give you guys two simple examples, and by that example, you will try to understand what is ridge regression, what is lasso regression, and what is polynomial regression, and why there is a concept called as regularization. Regularization concept. There is some concept called as regularization, and why we require actually regularization concept. This regularization concept means you have to give a penalty to your model whenever it is trying to perform not good. When it is not performing good, you have to give a penalty, and that penalties are called as L1 penalty, L2 penalty, or L1 plus L2 penalty. So I will explain you this. What is this L1 plus L2? L1 penalty, L2 penalty, L1 plus L2 penalty. Okay, and then our entire regression end to end will be covered, everything. Okay, so let's try to understand. First, we try to understand what do you mean by polynomial regression. Okay, so what is polynomial regression? What is the use of the polynomial regression? Okay, and why we require actually polynomial regression? Try to understand this way. Very interesting concept, guys, and try to understand why we create this kind of a polynomial regression and in which situation will require a polynomial regression. Okay, so let's understand this one. Let's give me one moment, and then by giving one moment, you will be able to understand what we are trying to do. And I will also explain you guys. So there are multiple concepts actually as well. So whichever concept we are trying to, like bias variance trade-off is there, we'll understand slowly. Like in one day, I don't want you guys to bombard with lot many situations in one time. So let's understand slowly, because usually this is not covered in one lecture. Actually, it takes 2-3 lectures. All right, guys. So let's try to understand why we require a polynomial regression and what is the use of this polynomial regression. Take a simple example. Take a simple example now. If I want to predict the salaries, okay, salaries of the people, and then according to the designations, according to the designation, if I want to find out the salary of the people, this is what the prediction model I want to fit out. Now let's imagine this way. So what I have to do? Simply, I have to find out the relationship. I have to plot my data. Okay. So let's imagine on x-axis, I am taking this equation. And here on x-axis, I will have a designation. So designation in the IT industry will be software engineer, SE, software engineer. Then something called as senior software engineer. And then something called as then team leader, lead software engineer. There will be manager, then there will be something called as director of engineering. Okay, director of engineering. This kind of a equation will be there. Then there will be director, portfolio manager. Then there will be head, HOD will be there. Everyone will be higher side. Okay, try to understand what kind of a salary they have. These salaries are in the lakhs per annum. Software engineer nowadays earn between 8 to 10 lakh, guys. 8 to 10 lakh per annum. Senior software engineer goes between 10 to 15 lakh. And then team leader obviously goes between 15 to 20 lakh. and then team lead goes between 15 to 20 lakh, and this senior, this manager goes between 20 to 30 lakh, 20 to 30 lakh, guys. And this director of engineering go earn between 40 to 50 lakh. And this director salary, guys, director of engineering goes between 50 lakh, and director, entire director, head, global head, okay, he earns between, guys, 1 crore to 2 crore. 1 crore to 2 crore or 3 crore package per annum. Per annum, okay. This is what he earns, okay. Let's plot this data. Let's start here. I am going to start with the 10. Let's here 20 lakh. Here is the 30 lakh. Here is the 40 lakh. Here is the 50 lakh. And here is, let's imagine, 80 lakh. And this is 1 crore. 1 crore, okay. And let's plot this. This is SSE, software engineer. Then this is senior software engineer. This team leader. This is manager. So this is a director of engineering. This is a global head. Okay, this way. And let's try to plot this data here actually. So senior engineer between 8 to 10 lakh. Software engineer. Senior software engineer between something 10 to 15 lakh, this way. Okay. So team leader goes somewhere here. Okay, team leader goes somewhere here. And then, guys, this guy goes, the manager goes somewhere here. Okay. So this director will go somewhere here near, and this head will going above, like this way. So this is how my data looks like, guys. Actually, this is how my data looks like. Okay. So actually, this is how my data looking like. So guys, if my data looking like this way, okay. So actually, these are not actual points, correct points. So correct point will be somewhere like this one. Let me draw it again. Okay. The correct point will be, guys, this way. Right. This is how the situation will look like, correct? So every time it is getting increased as the position increases there. Now, what I told you, guys, in regression, what we do, we try to fit a straight line this way, and this equation is called as y equal to mx plus c. Correct? Cool. So this is what we try to do. Now let me fit a straight line now here. Let me fit a straight line. So if I'm trying to fit a straight line, guys, here in this kind of equation now, try to understand what is happening. So if I try to fit a regular regression line, so guys, some differences are very high, like this way. These differences is very high, and this differences is close, but again the differences is very high, guys. So what this denotes, guys? What this denotes, that in this situation, when I have an exponential data, I have an exponential, because my salaries are increasing exponentially, guys. So try to compare this senior software engineer with the director. No choice. There's are no close by. Very, very exponential growth is there. 10x growth, 100x growth is there, guys. So I cannot compare this software engineer with the head of department or head of engineering, or with the director, global director, country head, India head, CEO, CFO, right? I cannot imagine even comparing. But if I try to find out this kind of a model, this kind of a situation where my data is exponentially increasing. So huge difference between the data, but I have to fit a model. I have to find out a prediction. So, but when I try to fit a this kind of a straight line, guys, this straight line will always give me error. Error margin will be very high. Error margin will be high. At that time, guys, at that time, my polynomial regression will come into picture. My polynomial, this kind of a situation where the growth is exponential, the data is exponentially changing. Okay, so polynomial regression will come into the picture, and let's understand how the polynomial regression will fit here. So guys, polynomial equation will fit this way. Okay, try to understand. This polynomial equation will fit this way, guys. So polynomial equation line is this way, guys. Try to understand. Now, when I try to fit this kind of equation, obviously it is very close to my data points, very close. And now I can do a prediction, and this is still called as y equal to mx plus c. But that's what is happening now. What is changing? What is polynomial regression? Guys, try to understand. When I say polynomial regression, it is same as exponential regression. Exponential regression, guys. Okay. So it is same as exponential regression. And exponential means what is happening? Whatever these variables are there. So let me write my simple equation. When I try to write multiple equation, m1 x1 plus m2 x2, okay, plus m3 x3, m3 x3, and so on, guys. So on, right? This is my equation. So this equation, guys, when I try to create this kind of curve line, okay. So this curve line is called as polynomial regression. Means what is happening? Whatever these features are there, guys, these features I am trying to square them or cube them. I am trying to change the degree. So guys, here the degree equal to 2. The degree equal to 2, thus it is creating this kind of a line. If the degree I am changing to the 4, I am trying to square them, cube them. So this feature simply I am trying to square them, guys. I am trying to square them. This x's I am trying to square them, or I can cube them. or I can take to the fourth power. I have to change the degree of my features. So when I change the degree, guys, my straight line will become a curved line. Okay. If I try to take the fourth equation, degree equal to 4, my equation will become this curve, this kind of a curve, guys. So by using this kind of a curve, I can fit a data very, very good fit best fit line. I can create a best fit line. So that is why we are using a polynomial regression, guys. In polynomial regression, I just have to do a transformation. I do a transformation my features. So my feature either they are squared, cube, or taken to the fourth power and so on based on the situation, based on the data cases. So I have to change the degree. That is called as polynomial regression. And you understood here the live example why we require a polynomial regression. So this way, guys, we can fit a polynomial regression and we can come to know that my regression model will perform better. So this is regression equation, and this is the situation where we require a polynomial regression, guys. All right. So everyone understood why we require, and in here the nothing is going to change, only the degree of the variable is going to change. Equation gonna remain same, y equal to ms plus c, multiple xs will be there, but only the degree here initially we do not have any degree, exponential power to these features, right? So this degree is going to change, x square cube 4 power. Okay. So this is what is going to change, guys. Now coming back to the last equation, why we need a regularization technique and why we need a this kind of a regularization techniques. What do you mean by regularization techniques? And why we require this kind of a ridge regression, lasso regression, polynomial. Now polynomial we understood. Now guys, try to understand. Regularization means we are giving penalty, L1 penalty, L2 penalty, and L1 plus L2 penalty. Now try to understand why we require penalty and what is the problem actually, what is happening. So let's understand this one. So very, very famous example, price prediction now. So you trying to do a price prediction. Now this time, guys, whatever price prediction you are doing a prediction for the house. All right. So guys, please try to stay with me and try to understand very, very important information. Why we have a regularization technique in mind or in place. Okay, regularization techniques. And what is this L1 penalty, L2 penalty, L1 plus L2 penalty? Why this kind of a penalties exist? What is their names? Okay, so let's understand. L2 penalties, guys. L2 penalty means ridge regression. Ridge regression. So this is called as elastic net. This is called as elastic net, L1 plus L2 penalty. And L1 penalty is called as lasso regression. Lasso regression. Let's try to understand why we require this kind of a regression or why we require this kind of a regression technique, why we need to penalize our model. Let's try to understand. Take example. There is very good example. This example, you will understand why there is a problem actually and why we require this kind of a regression technique there. So try to understand. So this regression techniques, what they say is, guys, this says that whatever the magnitudes are there, magnitude or the scale of the values, scale or magnitude values of the feature are not same, and that is the actually features are not same, and actually that is the problem. Okay, that is the problem. Try to understand. Now let's imagine you want to predict the price of the house. Now price of the house is my target now. Okay, this is my target column, price of the house. And for predicting, guys, for predicting the price of the house, I have this kind of a data. Let's imagine square foot. I have a square foot, then number of rooms. Okay. Then let's imagine whether the school is present nearby. Okay. So this kind of equation, or let's imagine this is a prime area or not. Prime area. And then let's imagine this is a metro city or not a metro city, right? Based on that also my prices changes. And then guys, number of this kind of a equation will be there. And then guys, and how old the price house will be there, age of the house, and now this kind of things will be there. Let's imagine, guys, when I'm trying to talk about the square foot, my square foot will be somewhere between, like say, I don't have something called as very small square foot. Like square foot will be like between 500 to something like up to 3000. We are just looking at the small scale houses. So the scale will be between 500 to 3000. Number of rooms could be between 1 to 10. 1 to 10, right? 1 to 10 number of rooms. School will be like yes or no. Yes or no, right? Yes or no will be like 0 or 1. 0, 1 scale, right? Prime area will be also 0, 1. Yes or no, right? 0, 1. Metro city also kind of a 0, 1 value. Guys, and based on that, I will have a price of the houses like a 1 crore, 1.5 crore, right? So, or 80 lakhs, 70 lakhs, and so on. This kind of a price of the houses are there. Now, try to look at the data. And what is the problem? Try to understand. Obviously, guys, try to understand. I have give you one situation. So, you will be obviously understand that every feature is important here, right? So, what is happening, guys, when I'm trying to put this equation into this equation, why is my house of the price? Now, let's understand. I'm putting something called a square foot now. the square foot is like, let's say this way, 1500 square foot. This is called as x1. Plus the number of rooms will be, let's say 5. Then plus, so prime area school, yes, school is present. So this is the prime area, let's say 0. No, not a prime area, okay, 0. Now, then guys, metro city, let's say yes, metro city, yes, means 1. Okay, and then guys, I am trying to predict my house. What is my house price prediction of 1500, 1500 plus 5 plus 1, 6 plus 1, 7. So 1507 actually. Now, what is happening when I'm trying to put my equation y equal to mx plus c? This is what going to happen. Numerical calculation will happen, guys. But in reality, actually, this is not correct, right? This is not right, correct. Why? Can anyone tell me why it is not correct? Like, or you can say here that my entire model is biased, guys. My entire model is biased. My entire model is biased because it is biased toward the square foot. The square foot, because the square foot area is very high. Try to understand. If I try to change the square foot, 2000. I'm trying to make the 2000. What will happen? 2507. 2507 means my changes, whatever the changes are there, there is an exponential change because of the square foot. And other things are contributing very less. Other things like school is present, prime area, metro city or not, this is contributing very less. But logically, it is very wrong. My model is totally biased toward the one feature. My model is biased towards one feature that is called as square foot of the house. Okay, and it is totally depend on that. And if I try to make a small change in the square foot, it is creating a high changes in the prices of the house, guys, in prices of house. Can anyone tell me like why it is wrong? Why it is wrong? Can you explain what is the situation? Why it is wrong and why it will not give you a correct house price prediction? This kind of equation, guys. Can you think of this? Very, very small logical difference is there. Can you tell me when I am saying that my model is biased, so it is biased towards the square foot? Half the answer I have told you. Can anyone tell me what is happening actually? Why this kind of equation will not give us a correct picture? So can anyone tell me what is the correct picture is not given here? What is the situation where we are missing out here when we try to calculate the price of the house? Any ideas, guys? Any suggestions why we are, I am saying that this kind of a model is biased towards the square foot? Okay, let's understand what people are saying. Scaling, correct, scaling, correct. So less weightages to other feature, correct, awesome, correct. Less, yeah, guys, less feature, less weightages to other feature. Now try to understand, guys. Actually, now let's imagine, let's take example. I will take one example from the Hyderabad city only, from the Hyderabad city. So let me write this equation here. In the Hyderabad city, guys, I think most of you will be aware of the Hyderabad. So let me tell you Hyderabad city example. Guys, if I am trying to take a flat, if I'm trying to take a flat, okay. So if I'm trying to take a flat and my area is, let's say the prime area, right? I told you that prime area matters, right? Prime area matters. I will tell you like how prime area can matter and how big the difference can it mean. So let's imagine you trying to purchase a house in the Banjara Hills. Banjara Hills, guys. So whosoever are from the Hyderabad, Andhra Pradesh, Tamil Nadu, not Tamil Nadu, actually nearby cities, guys, AP or Telangana, you will guys very well aware. So Banjara Hills is like a Manhattan in the New York, right? So if you try to take a flat in the Banjara Hills, and let's imagine you guys are trying to take a flat in one area, which is, let's say, JNTU College, okay, JNTU College, Nizampet, JNTU College, Nizampet. Now try to understand. Now the situation is same, guys. I am having same square foot, 1500 square foot, plus I am in number of rooms, let's say 5 BHK I'm looking at, plus I have a school present, yes. And then guys, plus whether it's a prime area for Banjara Hills, yes, the prime area will be 1. And the metro city, yes, it is a metro city. So my equation becomes this way, 1508. And same situation here, what will happen? Same will happen and same equation will be here, like 1508. But which is wrong. Can I get a same price flat which I can afford in a Banjara Hills? So let's imagine in Banjara Hills, whatever 5 BHK flat I am taking, whether it will cost me the same, guys, which I am trying to take in the JNTU College or Nizampet area. Can whosoever from the Hyderabad, can anyone tell me? So not possible, right? Not possible. So whatever the cost of the Banjara Hills flat is there, right? So can anyone ping me like you if you are know these areas, right? Banjara Hills is very, very prime area and JNTU is not that prime, right? Nizampet is not that prime area, or Kukatpally area, right? So obviously, if I try to take a flat, same configuration flat, 1,500 square foot, 5 BHK and something, it will cost somewhere around 1 crore here, 1 crore in JNTU near Nizampet. And if I'm trying to take same in the Panjakutta area or Banjara Hills area, guys, it will cost me around 4 to 5 crore. 4 to 5 crore. Because why? The square foot is same. But my model says that whenever there is a change in square foot, the house should change, housing price should change. But actually the prime area is changing only. The area is changing, and this area, guys, it is creating exponential change in my pricing, right? Exponential change in my pricing. 4-5 crore, and here only 1 crore. Same configuration, same number of rooms, same school is present. Prime area is also there. Metro city is same, guys. But the prime area is making much difference, right? So this is the reality. This is the reality, and this reality should also be understood by my model. Right? So that means my model is biased as of now. When I try to fit this equation, fit this equation in kind of a y equal to mx plus c, and my model it is only looking at the numerical features. Try to understand, it is only giving the differences. If the square foots are high, it is only giving preference, and that is wrong. That is wrong, and that is why, guys, I have to bring something called as regularization techniques. Regularization technique, and these, guys, regularization techniques, okay? So these regularization techniques are called as L1 penalty, L2 penalty, and L1 L2 penalty. What they says is that can we do something regarding the magnitudes? So this kind of a magnitudes are there. Can we do something around the magnitude so that my model is not biased towards any feature? So this biasness has to be removed, okay? So that is why we have something called as ridge regression, lasso regression. And whenever people say that ridge and lasso will not perform only singly good, so we take a combination of ridge plus lasso, that is called as L1 plus L2 penalty, that is called as elastic net, guys. Elastic net, okay? So let me write down the formulas now. So now everyone is very, very clear, right? So why my model is biased, and when I try to put this kind of a situation in y equal to mx plus c, and that is why I need a regularization techniques, right? So this is what everyone understood now. Okay, so let me rub these things and let me write it here. Very quickly, okay? Very quickly, let me write this thing. And guys, I know it is a very vast topic actually. So what do you mean by L1 penalty? What do you mean by L2 penalty? And what is L1 plus L2 penalty actually? So guys, what they do is they try to say that we can do something regarding the magnitude. So what they're doing in L1 penalty, guys, in L1 penalty, let me write the equation. So I write this way, yi minus y hat, yi minus y hat. And whatever the loss equation is there, guys, I'm trying to add or minus something which is called as lambda. Lambda is my learning parameter into, guys, into I will add a L1 penalty. L1 penalty talks about, guys, L1 penalty talks about the, I have to take the absolute values of the magnitudes, and these magnitudes are called as like M and C, right? Magnitudes are M and C, or I can write the same thing, y equal to mx plus c. I can same thing can be written in this way, y equal to beta sub 0 plus beta 1 x1, So this beta 0, so this mod I am taking is called as beta, right? Betas. So betas, whatever this beta i's I am talking about, what are the m's? This m I am talking about. This m are magnitude, right, of the features. So m I am talking about. I am taking the absolute value, and I am trying to multiply by something called as hyperparameter. So this hyperparameter is a small portion, some constant portion like this one, 0.1%, 0.2%, or 0.3%. That percent of this magnitude of summation values. So all the magnitude, all the betas, all the m's which are related to this one, square foot, number of rooms, and all these things. This portion I'm trying to add in my this portion, guys, I'm trying to add in my loss function, and by using this kind of a addition or subtraction, okay? So this kind of a subtraction to my loss function, I'm giving penalty. I'm giving penalty, and whatever the loss is there, I'm trying to reduce that loss, and by introducing this penalty, this is called as L1 penalty, and this is same thing is called as lasso regression. Lasso regression, guys. So this is called as lasso regression. Lambda into mod of betas. All the betas are the coefficients or the magnitudes of the features, guys. So this is what it is called as, and by introducing this penalty, I am trying to regularize my model. So whatever the biasness was there, that biasness is removed, guys, by using this kind of equation. Now try to understand what do you mean by L2 penalty. What do you mean by L2 penalty? In L2 penalty, guys, they think that, so by this kind of equation, yi minus y hat is there. So this kind of equation, yi minus y hat, I have to make a square of this magnitudes. Lambda will be there. This lambda is a hyperparameter. So lambda is a percentage into summation of all the betas, I equal to 1 to n. And I have to take a square of betas, guys. Square of the betas. And this squaring, if I try to take the square value, and then I am trying to add or subtract from my loss equation. So this is called as now ridge regression. Ridge regression, and which is called as L2 penalty, guys. L2 penalty. So this kind of a penalty, if I try to add, guys, so this will become, my equation will become very nice, and my biasness will be removed. Okay. And some people says that don't go with the L1 and L2, go with the both the combinations. Okay, both the combination of L1 and L2, guys. At that time, what will happen? L1 and L2 combination. Let me rub these things and let me write it here. L1 and L2 penalty. So they will write like this way. Okay. L1 plus L2, which is called as elastic net. So they will try to do this way. Yi minus y hat minus, guys, minus this lambda is always there into alpha minus 2, okay, divided by alpha minus 2 divided by some portion, alpha minus 2 divided by some constant, okay, and into L2 plus lambda into alpha into L1. So this proportion, lambda into alpha into L1. So they are using both the combination, both the combination. So this is called as elastic net, L1 plus L2. Okay. So this kind of a equation we are trying to add, guys, and then which is called as the biasness will be removed by adding this kind of a situation. Some portion, this alpha is what? Some portion. If I am trying to take, let's say 100% proportion is there. Out of that, alpha minus 1 means if I am trying to take this L2 penalty as 50%. So obviously the other penalty will be taken 50%, right? Alpha minus 2 plus some constant will be divided, and this learning parameter is always there, proportion. Yeah, lambda. So lambda percentage is always there, guys. Or you can say if I am taking 60% of my L2, obviously alpha minus 1 will be 40% of the L1, guys. So this kind of a combination they are trying to add to the loss equation, and by trying to add this loss equation, guys, they are trying to make a biasness, remove the biasness. Okay. So this is beta I mod, this is beta I. So magnitude square, and they are summing up and they are trying to add, guys. Okay. So this is what called as L1, L2 and regression, ridge regression, lasso regression, and L1, L2 elastic net regression, guys, of penalty. And you understood why we require regularization technique, because to my model is become biasness towards the magnitude. That's why I require them then. All right, guys. So everyone understood this concept? Any doubts, any questions as of now here? So let's make a code walkthrough, and we'll try to understand one concept which is called as gradient. Now tomorrow we'll try to start with the gradient descent. Today we'll try to understand with the logistic regression. So if the time permits, so let me unshare this screen and let me show you my entire notebook. So we can make a code walkthrough. No, guys. Before that, let me explain you one more thing, that entire called as model life cycle actually. So quickly understand the model life cycle, how the model is built actually, and then we can go here and try to understand the code walkthrough. All right, guys, can you guys confirm that you are able to see my presentation and you are able to see the data life cycle, right? All right, guys, thank you. Rashmi ma'am, thank you. Thank you, guys. Thank you. Karthika ma'am, thank you. So guys, try to understand the model life cycle, how the model life cycle is done, how the model fitted actually, how the model is fitted, and how the thing starts. Okay. Try to understand, guys. This is a flow diagram, data flow diagram, and try to understand what are the steps involved in the model building. Okay. So let's imagine this way. So how the everything starts. Thus, here is the start. Okay. Starts with the business understanding, means they will give you some problem to solve. Some problem to solve, they will give you. Let's imagine they are asking you that you have to predict the customer, you have to predict the customer category. Customer category prediction you have to do, customer category prediction, customer categorization you have to do. So this is the problem they have given you. Okay. So let's understand this way. So now what is going to happen and what is going to start now? The problem here is the problem. You have to do whatever customer data is there. You have to do a categorization, customer segmentation, customer categorization. You have to do. Now, what is the first step? How the things will start? Now the thing will start here. So what you have to do? You have to do a data acquisition and understanding. Data acquisition and understanding. So you have to collect the data first. First thing comes is the data, guys. First thing in the model building, is the process flow diagram. First thing comes as a data now. So what do you mean by data? You have to collect the data, guys. You have to collect the data. So for data, there could be multiple sources. So data, there could be multiple data sources are there. One is the data source, could be a database in your company, could be a database in your company, or could be a streaming pipeline. If your company is doing live streaming, if their company's data coming on live basis, everyday basis. So I told you the example of sensors. If your company is doing sensor, or let's imagine you are an Amazon company or kind of a company where every day your database is getting updated. Your database every day, new customers are coming, old customers coming, new transactions are done, right? So that means you have a live pipeline. Every day your databases is getting updated. So these are some data sources. So data source could be database tables which are stored, or could be a pipelines where every day new data sources coming, Could be the environments, like you can do a web search, web scraping. You can do a web scraping, you can go Wikipedia, you can go the internet, you can do a different thing. And this kind of a sources are there, or you can create a CSV files, you can create a TSV files, you can create a spreadsheets, Excel file, and all file. So these are your data sources there. These are your data sources. Let's imagine these data sources are there. And then what will happen? So data acquisition is complete now. The data acquisition part is complete. Data acquisition now. So once you have a data acquisition part, now what you have to do? Second part. Guys, second part is called as data wrangling. Here, this part. Now let me denote this part with a different color now. So second part you have to do this way. Once you have data, guys, what you have to do is you have to do a data wrangling. Whatever data you collected, data wrangling and data cleansing. Data wrangling, and then guys you have to do something called as data EDA. Can you guys tell me, like, wrangling or cleansing? Data cleansing means what could be the things we are trying to do here in data wrangling or cleansing? Have you guys ever heard, like, what is a data validation? What is a cleanup? What is the visualization we are trying to do? What is kind of a cleanup we try to do? Anyone can give me any example, like what type of a wrangling techniques, what kind of a cleaning techniques we are doing on the data, guys? Because whatever data is there in the database, as it is, I cannot feed that data to my model. I have to do some kind of a cleansing, wrangling, cleaning. Right? So can anyone tell me the example? Yes, ma'am. Correct. Karthika, ma'am, correct. Pre-processing we have to do. But can you guys give me example? Like what kind of a pre-processing? What kind of a things I'm looking out here in the pre-processing? What are the steps? Or what is the thing I'm looking for? Can anyone tell me the solid rules? Like what I have to check, what I don't have to check, what I have to drop, what I have to find out. Okay. Missing data. Awesome. Shinde sir, correct. Professor sir, correct. So guys, what I have to do is I have to find something called as NA values. I have to find out zero values. Correct. Awesome, guys. Awesome. Correct answer. Filtering, sorting. Yes, guys. Yes, guys. Correct, guys. Correct. Your answer is correct, guys. Thank you. Nice answer, guys. Inconsistent data, incomplete data. Correct, guys. Correct. Handling duplicates. Correct. Awesome, guys. Zero values, NA values, then duplicate data. Okay, duplicate data I have to do. Then what I have to do is, guys, if there are any outliers, correct? So you guys are heard of the outliers. Outliers invalid values, correct? In duplicate value, correct, man? Awesome. Bharti ma'am, Rishmi ma'am, everyone correct, guys, correct. Thank you, guys. Thank you for answer. So what you have to do is, like, you have to remove the zero values, NA values. You have to what you have to do is you have to perform imputation, normalize, correct? Awesome. Normalization, Vaishnavi, correct, awesome. So guys, what you have to do is you have to remove the outliers also. Outlier are a value which are far away from the mean, Like if your entire data set is out here and one value is lying away here. So that kind of a value is called as outlier. So you have to remove this outlier. You have to remove zero values. You have to remove NA values. You have to remove duplicate values. And what you have to do is, guys, in this kind of a thing, you have to also understand if we have to do any kind of a data transformation. Data transformation means if any data types transformation. Data type, you have to change the values from the float to integer or text value to numericals and all. Okay, guys, always try to remember that whenever we have a text category data, we have to remove that text category data and convert that text category data to the numbers. If I have a text data, that text data has to be converted to the number, then only I can feed that data to the model. Means imagine you have a category called as gender. In gender, guys, you will have a value like male, female, or transgender. Okay, 3 categories. So what you have to do is, like, you have to do 0, 1, 2 encoding. So we have to create this kind of a encoding, or what we can do is there's a concept. That concept is called as, guys, data duplication, get dummies, or data label encoder. Okay. So either you create this kind of a numbering system, or you add a new columns, which is called as like male. Then there will be something called as female, okay, and transgender, and then it will be like shown. If the particular record belongs to a male, it will be shown 1, and everywhere it will be shown 0. Like if it is a female, then 1 here, otherwise 0. This kind of a columns will get added. So these are the two ways. Or you can give a number, male 0, female 1, and transgender 2. Okay, this kind of a things you have to do, guys. So this kind of a transformation I have to do, and all the data convergence, if number has to be corrected. Okay, all these things. And guys, last thing what I do is EDA. Can you guys tell me what is EDA? EDA, what do you mean by EDA? Then we'll come back to this feature. Okay, once these steps are done, then my model will come here, guys. The data will be cleaned, and then I have to start this topic here. Yeah, extraction. Correct. Awesome, Markiman. Okay, so try to understand. EDA means exploratory data analysis. Guys. Exploratory data analysis. And EDA stands for exploratory data analysis, guys. Exploratory data analysis means, guys, this is the same thing. Okay, guys, transformation, correct. Exploratory data analysis, correct, guys. Awesome. Means, guys, I told you two type of a relationship you have to find out. One relationship is between the target and the feature, and second relationship you have to find out between the among the features, and you have to do a multi-collinearity check. So all these things are done by using the visualization tools. By using the visualization means using the graphs. Okay, that is called as EDA part. That will start. And guys, once you do this EDA part, guys, then next step, let me write the steps here. Okay. So this data acquisition is the step 1. So the data sources, then this is the step 2, guys. So you have to do data wrangling, cleaning, and then you have to move to this one part now. Feature engineering. This is the step 3. You have to do feature engineering, means which column to choose, which features to choose. If you have to merge some columns, you have to remove some column, you have to drop some column. That part you have to do, guys. That part you have to do. And then once you are done, guys, once you are done, then that's the step 4 will start, guys. The step 4 will start. So step 4 is, guys, here, model training. The step 4. In model training, guys, what you have to do is, whatever the data set is there, you have to divide that data set. That is called as sampling techniques. So there are 3 sampling techniques. Actually, one is holdout method, one is called as k-fold method, and one is leave one out. I will explain you whenever get time for this kind of things. So try to understand what do you mean by this. Whatever data set is there, let's imagine this is your 100% data set. I cannot give entire my data set, guys. Entire my data set to the training purpose. What I have to do, I have to hide some portion. Let's imagine this splitting. Data splitting has to be done. Data splitting. So what splitting I have to do? Either I do a 70-30 splits. So 70% portion goes to the training purpose, 30% goes to the testing purpose. Or you can do a 80-20 split. 80-20, or you can do a 75-35. Sorry, 75-25 split, guys. Okay, this kind of a split you have to do. You have to hide one portion. We cannot give entire your data set. And then once whatever the training data set is, your training data will start. Your model training will start. Then in model training, what you have to do? In model training, guys, you have to call your functionality, call your model from the sklearn library. You have to import the libraries. So you have to call your model. Let's imagine here we are calling regression. So you say regression, linear regression. This is a function, this kind of a model you'll call. You'll call this as a model equal to linear regression. And then you'll say model.fit. Model.fit. You'll simply say model.fit, guys. And model.fit is means your training started. Okay. This is the 4th step you guys will do. And once you do this step, guys, your model get trained. This code you will be calling. And then, guys, your model get trained. Once your model get trained, guys, what you have to do is, you cannot directly go ahead. You have to do a evaluation. Model evaluation. Before model evaluation, once you do the training, guys, there is one more step. That step is called as saving your model. Save your model. Okay. You have to save your model first before you do a evaluation, guys. Okay. So save your model by using kind of a library called as Pickle. You have to save your model. Some kind of a file will be saved like this way. Finalized _model dot pkl. This extension will be there. And this kind of a file will be saved in your drive. Okay. So that thing is called as model saving file. Model saving. Okay. That is the 5th step you have to do. Let me write it here. The step number 5 will be model saving. Then, guys, you have to do model evaluation. Then in the end, 6th part is model evaluation. And you guys already told you, right? I already told you what is the model evaluation. You calculate R score. You calculated adjusted R score. Okay, adjusted R score, you calculate MSC, RMSC, or something called as F score, which is the F score. F score is, guys, this way: SSC divided by SSR, the ratio of different errors. Okay, so that is F score. So this kind of a formulas you can use, and you try to find out whether model is good or bad. Okay, your training accuracy, testing accuracy, that will come in the model evaluation part. So that is the step number 6. Okay, guys, and this is not the end, guys. This is not the end. Let me rub this thing down. This is not the end. So this part is not the end. This is the development part, guys. So this is the development part. So this is called as development, AI development or ML development. Guys, then the actual picture start. When you are completed the model training, testing, evaluation, your model is giving 95% accuracy, guys. Then what is happening is your deployment part start. Your deployment part start. In the deployment part, guys, you have to create a model file, a model.pickle file, and then you have to create one kind of a file called as requirement file, which contains requirement.txt, which contains all the packages required, all the packages and their versions, like this way. If you are using NumPy package, NumPy equal to so 1.1.0, this kind of a package means dependencies. To run your model, what are the dependencies? That dependency file you have to create. You have to create your model file, guys. Obviously, if you remember or if you know that, guys, whenever you are using any Play Store app, or whenever using like this kind of a face detector app, so this face detector app, you are not running Python code, right, in the background, or you are not running AI code. You are just running some application, right? So that UI, user interface, has to be created, right? UI part has to be created. That part comes in the deployment part, guys. Deployment part. So your model file is required, your requirement file is required, and you have to develop the UI. Either you develop the UI using the HTML or CSS user form, or you can do an Android development, or you can create using the Flask app. Using the Flask app, you can create a something called as APIs. So API creation will happen, guys, here. So API creation will happen here. And once you create the API, once you create, guys, API, then what is going to happen? What is going to happen? Then, guys, then your model is ready. Your model is pushed to the production. So you have created an application. You have created one app. So that, let it be Android app, mobile app, or could be a website. Could be like this kind of a website, www.diabeticprediction.com. So this kind of app, right? So this kind of application website you have created. Then, guys, this portion comes in. This is the last portion. This is the step number. This deployment part is step number 7, and this is the last step. Deployment part is called as step number 8, guys. So let me draw this. This is what is happening actually. So this part is the development part, and this is called as deployment part, guys. This is very famous. This is very famously called as AI ops. AI ops or ML ops part, guys. ML ops. So when your model is built, guys, you create a kind of a requirement file, dependency file, your model file, and your UI file, and that is taken and that is pushed to the production system. That is pushed to the, your code is pushed to the production system, and by using this kind of a UI or Android app or AL app or iOS app, your model is, guys, now consumed by the last end user. The user is consuming your model. Then that is not the end, guys. That is not the end. Your model is continuously monitored. Your model is continuously monitored, watched 24/7. Watched 24/7. Whether your model is giving the required accuracy, or whether your model is performing that with speed, the inference with the speed. Okay. So this part, this portion is continuously going on. Continuously going on 24/7. There is a special team. That team is called as ML ops team or AI ops team, which monitor your models continuously. And once your model is not meeting the criteria, it will again come back to the development part. And again, you have to develop or retrain your model. Retrain your model. That is why this life cycle is going on, guys. This life cycle is going on this way. Create, build the model, deploy to the production system. If some error occurs or some monitoring happens, if the your model is not up to the mark, again come back to the retraining, again development, again push back to the model, guys. So this is entire life cycle is going on, and this is how you build a model. And after building model, job is not done. Only development part is done. The AI ops or ML parts is continuously running, guys. Continuously running in the background. All right, guys. So this is what is called as data life cycle of the data science project or the ML ops part or AI ops part, guys. All right. So, guys, we still got a 5 minutes. So let's make a code walkthrough, at least for the regression model, and then tomorrow we can maybe start with the logistic, and we'll try to understand the decision tree as well. Okay, tomorrow. So this part is very vast, guys. Actually, regression part is very vast. So that is why it takes time to understand the concept, because I don't want to rush you guys through the topics. So once your topics are clear, once your entire basics are clear, guys, Once you know how to build the model, what are the basic concepts, how to analyze the error, how to perform the model validation, what is this feature engineering. Guys, there is a separate course. There's a separate course actually in the Google. They dedicated one course for the feature engineering and feature implementation, right? So that kind of try to understand the severity or try to understand the topic importance. Okay. So one special course for 10 hours they have designed for feature engineering. I've done that course. That's I to understand. And to fit that knowledge into this kind of a small sessions is not possible. So that's why I'm trying to focus more on this knowledge. Okay. Once you understand this, then it will be very simple part. The algorithm working can be understood very easily, guys. So let me stop sharing this screen and let me share my code window with you guys and try to make a simple code walkthrough. It will not take more than 5 minutes and we can conclude our session today then. So let me share my code window with you guys now. Just a moment. All right. All right, guys. So just quickly give me confirmation. So you are able to see my Jupyter notebook. All right, guys. Thank you for the confirmation. Now try to understand actual code walkthrough. So it will not take much time. Thank you, guys. Thanks for Vaishnavi ma'am, Rashmi ma'am. Thank you. So guys, let's try to understand. Yeah, Anusha, thank you, ma'am. So guys, let's try to understand how to build a model now, actual code. So first thing what I have to do, I am here, I am just importing the library, guys. Let's try to understand. I am using pandas, I am using NumPy. This is for the data cleansing and data manipulation. Data cleansing and data manipulation. These libraries I am using, manipulation, okay? So then guys, from sklearn library, what I am trying to do, I am doing a standard scaler. Standard scaler. I tell you what is this standard scaler. Actually, there are two concepts actually. Standard scaling for the scaling, right? You remember the housing price prediction. So we have to do something around the scale of the magnitudes, right? Scale of the product. So there is something called as two types of concept are there. One is called as standardization, and something is called as, guys, normalization. Okay. So something is called as normalization, guys. Very quickly, let me tell you. Standardization means we using the z-score or t-score formula to bring back the transformation, to perform the transformation on the values, guys, on the features. By using this, guys, we try to bring the data in the lower scale, maybe in the scale of 0 to 1 or in the smaller scale, whatever the higher scale data is there, we try to bring that into the lower scale. So in standardization, guys, we use a z-score like this one, x minus x bar divided by sigma by root n minus 1, or in t x bar minus mu divided by s by root n. So I don't have to explain this because you guys are already aware of this stats concept. So z-score and t-score, these are the standard variation, z distribution, t distribution. And by using this kind of a formula, guys, whatever my values are there, whatever the data is there, entire features are there, that the data features, the values which are the like square foots and all, so thousands of values in the scale of the thousands and hundreds scale, I'm trying to bring them in the lower scale, like 0 to 1 or 1 to 10 scale. Okay. So this kind of a scaling is done. That is called as standardization technique, guys. Okay. And then second technique, guys. Second technique is called as normalization. And try to understand what I try to do. In the normalization technique, guys, what I try to do is, in the normalization, I try to bring the data in the scale of 0 to 1 without changing the meaning, guys. Whatever transformation I'm doing, I'm not changing the meaning of the data. Okay, that is a very important. If I have some data which is in the square foot, that data's meaning will not be changing, right? That data's distances will not be changed, but still they will be doing the transformation. Let's try to understand normalization means what. I try to fit the data into this normal curve, guys. Everyone knows this normal curve where mean equal to 0 and standard deviation equal to 1. This is called as standard normal deviation, standard normal distribution. So this kind of a normalization I'm trying to do by using the normal distribution formula. I can use a min max scalar formula. So the value x minus max divided by max minus mean. This kind of a transformation I'm trying to do. I use a different distribution formulas and try to bring the data into this kind of a format, guys. This is symmetric format. If I try to cut this data, this part and this part is symmetric, the mean is 0 and standard deviation is 1 for the data, and data ranges between 0 to 1. This kind of a transformation is called as normalization, guys. So for that purpose, I try to bring this kind of a standard scalar, guys, And then, guys, you already aware this ridge regression, lasso regression, elastic net, and our normal linear regression. This I am importing These models I am importing from linear regression, sklearn.linear model. Okay. And then I told you trend test split, because whatever data is there, I cannot provide that entire data. So I try to do this kind of a splitting 80-20. So 20% portion I will hide. I'll not give it to the training purpose, only give a 80%. And this remaining portion, I will try to test my data for the accuracy. So that kind of a portion, that kind of a things is created by using trend test split, guys. And then matplotlib and pyplot and seaborn for the visualization purpose. I have to do a visualization, guys. Guys, this is the end-to-end project. So you will be seeing all the implementation out here. So let's try to understand. And then, guys, I have created manually in the Python code. So adjusted R score. Okay. So R score formula, you already know the R score formula. 1 minus R square minus 1. 1 minus R square minus 1. Okay. So 1 minus R square minus 1. N minus 1 divided by N minus P minus 1. So this kind of a formula I have created manually here by using custom user defined function. Okay. So you can refer to this one. I'll not go into detail. Now, guys, what problem I'm trying to solve? See here, I'm first importing my data. So this data is admission prediction. I try to understand the data. Guys, it will not take more than 5 minutes. I know it's already time. I'll not cost you more than 5 minutes, and let's finish this code work. Very, very simple code work is there. So first I'm trying to import my data in the data frame, guys. In the data frame. So I'm creating one data frame, and the data frame is I'm importing read underscore CSV. I'm calling this file, and this data is called as data frame now. So I'm trying to look at the head means top 5 records. Top 5 records I'm trying to check. Now look at the data, what I have. So if you try to look at the data, guys, what is my target here? This is my target. Why? My target is what is my chance of admission into the university. In the universities. Okay. If I am going for the MS, I'm trying to do a Master of Science or something post graduation. So this kind of a characters are there. This kind of a features are there. What is my GRE score? What is my TOEFL score? What is my university rating? What is SOP? What is letter of recommendation? What is my CGPA? And whether I have done a research, yes or no, 0, 1. Okay. On the basis of this, guys, on the basis of this, these are called my X. These are my X, and this is my Y, guys. This is my Y. This is my target, and X are my features. Okay, these are my features. And basis of this, I am going to put this equation y equal to mx plus c, guys. Okay, and then I'm going to predict my chance of admission. This is what the data looks like, guys. When you try to look at the data, guys, this serial number column is not making any sense. This is just giving me the row number. So I can remove this kind of a things. Or you can say the TOEFL score. TOEFL score are in the float values, guys. These are the float values. I don't require float values. I can convert them to the integer data type. Okay, so then you can see if the research column is looking like this one. Yes, no, yes, no. Obviously, I have to convert them to 0, 1, 0, 1, 0, 1, 0, 1. Okay. So this kind of a transformation, guys. Or you can see here one more thing. You can see here NaN values. NaN values are there. So this kind of a remove NaN values, remove 0 values, or perform this kind of a transformation. This is what I'm going to do. And I'm going to remove the outliers as well, guys. Outliers as well. Okay. Access to XLR LMS, guys, it is available. Chandana will address this thing, guys. Dharma sir, Chandana will tell you like how to access it. She will explain. Okay. So wait for code walkthrough and we'll explain like this thing. Okay. So guys, this is what the data looks like. Let's understand what I'm trying to do. I'm trying to make a describe data.describe. Describe will give me a 5-point summary, guys. 5-point summary. Like what is my mean value? What is my standard deviation? What is my max value? What is my count? So if you look at the count, guys, some values are missing. See here. So my total count, my total data set is 500, but some columns are 485, 490, 485. Okay. So that means some missing values are there. That is what they're trying to see here, guys. So they're trying to remove. Okay. They're trying to remove the NA values. You can see here the code. Data, university rating, TOEFL score and GRE score. They're filling the NAs. Fill NA with the mode, mean and median, guys. So this kind of a filling I'm doing. Okay. First, data cleansing part I'm trying to do here, guys. Then I'm trying to understand what I'm trying to do. The serial number column, which was not important, I'm remove that serial number column. Now this is my data is clean, guys. This is my data clean. This is my X and this is my Y. Now I'm trying to plot my data to find out how the distribution look like, whether my distribution is normal distribution or not, and whether the outliers are present. Okay. So when I'm trying to plot using the plt.plot distribution plot, guys, and I'm taking one column, I'm putting one loop for loop, and I'm passing through the column names, and I'm trying to plot this function. sns.cborn.displot, this create a distribution plot. Now, if you try to look at this data, guys, some distribution having a this kind of a peaks actually. This kind of a this distribution having this kind of a peak. So this peak means these are the outliers present. Okay, outliers present. So which is going above my normal distribution value. Okay. So these values I have to remove. This is what I am going to do by using the visualization. Now, if you try to create this kind of visualization, guys, so I have to remove these values. So try to look at these things. So when I'm trying to do, once I fill NA, remove NA, and if I try to look at the data, guys, I'm trying to transform. Okay, I can check this and can remove the outlast. Now I am calling this transformer, right? Standard scalar, and then when I call this standard scalar, and then standard scalar dot fit transform x. X means all my features. All my features means this all the columns, guys. Yes, guys, I will share this sample code. Okay, don't worry. So I am taking all these columns. Okay, until here from GRE score to research, and I'm trying to convert because the scale is different, guys. One is in the 300 scale, one is in 100 scale, one is like 1 to 10 scale, one is in 0 to 1 scale. To bring back to the same scale, I'm doing a transformation now to the data. See here, standard scalar, and standard scalar dot fit transform x means all my columns. And once I do this, guys, I told you that we have to check the multicollinearity VIF function. Remember this VIF function. So I'm calling this my VIF function. See here. So VIF function and the feature name. So none of them is above 5. If there is above 5 score, I will drop that column accordingly. Okay. Once I created this, when I check the multicollinearity, when I remove the outlier, when I did my data cleaning, I've understood entire feature selection, guys. And then last step is split my data like this way. I'm calling train test split. I'm passing my x scaled values because these are transform values, y values, and my split is guys this way 75 25. 75% is going into the training, 25% I'm hiding for the testing purpose. Test size equal to 25. Random state, this is a random number generation. Okay, so this kind of a splitting I've done. Then guys, I will call my model simply. So see here, I'm calling linear regression. This called in the variable called as regression variable. Linear regression model I'm calling, and then I'm saying fit dot fit and passing my train data. X train, Y train, guys. And my model training is done simply. Then guys, I'm saving. I told you that second step is save your model file. So I'm saving this model file, finalize model.pickle by using pickle.dump. I'm calling this as a regression model, and then I'm saving guys in read write mode. Okay. Once I save, guys, again load back the model. Again load back the model. Pickle.load file name and load the model. Okay. So once you load the model, then do the prediction, guys. Then do the prediction. Okay. So this is how in the corporate it is done. You directly once you feed the model like this one, regression equal to regression model, regression dot fit train test, then don't go for prediction. First save the model. First save the model and then load back the model again back. Load back the model, then pass the data, guys. Here I'm manually passing the data. See here. I'm passing the data, scaling data like 300, 100, 55. These are GRE score, TOEFL score, university rating, SOP, CGPA, and research value. And then I'm saying what is my chance of prediction. See here. 92% chance of prediction, guys. Okay. So this is how. And I can check my R score now. The R score is created by regression.score, xtrain, ytrain, 84% score. Very nice score I have achieved, 84%. And I can call my adjusted R score. See guys, adjusted R score will be always less. So R score and adjusted R score are also showing good values. So 84% and one is 83%, guys. Looks very good. So, and then adjusted R score is looking good. So I can create a regularization technique also. Simple, same thing is there. So call the lasso regression. In guys, I told you like you have to pass some variables. Like pass variables means alpha. Remember this function. Remember this whenever I said like one kind of a lambda parameter and then L1 penalty or lambda parameter into this kind of a L2 penalty, right? L2 means squaring. So this lambda is called as alpha here, that alpha lambda. And then we are adding this to my actual loss function, right? Yi minus y hat. So this is what is happening. So this kind of a lambda or alpha, that value I have to pass here. Cross validation I will explain you later on. Maximum iteration means how many times you have to perform this model iteration, and normalize equal to true or false means normalization, whether we want to do a normalization or not. Okay. So this kind of a lasso regression I am passing here, and lasso, once I call this lasso function, say same thing, lasso dot fit pass x train y train, and like take the lasso dot alpha, like how much is the alpha value they are taking here. Actually, I gave none, and then I'm trying to find out this using the cross validation. What is the best parameter for alpha by using this one? Okay, this is how we can fit, guys, and I can check my score also. So let's understand this one. Lasso dot fit, and I can check the score. Score is 75%. R score also I can check. R score is also coming again. Same way I can fit my ridge regression. Ridge regression equal to CV alpha, the same thing, and try to fit regression dot CV, fit the train test, and that's it, guys. I can check my alpha score. I can check my model score also, R score. Okay, elastic net, same way, elastic net CV. Call the function, pass the alpha, and I say elastic net dot fit, pass x train, y train, guys. And you can check the score also. So you can check here ratio, L1 ratio, how much L1 ratio they are taking. They are taking 0.5%. L1 is 0.5% L1, the remaining percent will go to the L2. So elastic net, okay. And then guys, this way you can check the score also. So if you try to check the regression score, it is coming 75, 75, 75. All the scores are coming 75 near enough. Means you don't require this one. And last guys, last thing is polynomial. So simply what I have to do in polynomial guys, whatever data is there, see here, I am taking the same data, position and the salary data. So what I'm trying to do is, you don't have to create any separate thing. Just call your model this way, linear regression dot fit. And whenever I try to fit the model, you can see the model, normal linear model is not fitting correct, right? So it has a gap. That's why what we're doing is something called as polynomial feature. Polynomial feature, call polynomial feature, and within the polynomial feature function, guys, pass the degree. Like whether you want to, yes, guys, we are winding up now. Okay, last 1 minute and we are wind up now. Okay, so polynomial feature, and one you pass the degree, like we want to square the data or square cube or something like that. And once you create this kind of a feature, guys, transform your x and that's it. Polynomial dot fit xy, and your model is fitted, guys. Your normal regression model, and that's it, guys. Okay. So we have seen the implementation, one line implementation is there, guys. All right. So this way you can fit entire regression, polynomial regression, ridge regression, lasso regression, or your normal regression. You can check R score, adjusted R score. You can do a EDA, you can do a entire data cleansing, and this is end-to-end model, guys. End-to-end model. Okay. All right, guys. So I know it is late, 10 minutes late. So let's wind up our session now, conclude for today, and we'll continue tomorrow with the logistic. We'll try to continue with the decision tree and so on, guys. All right, guys, I think you enjoyed this session, entire end-to-end application, all the concept, how to perform model evaluation, what is data life cycle science, how the things are working, what is the penalization, what is penalties, how the regression model works upon. So hope you enjoyed today's session as well, guys. Very intense session, I can understand. So guys, thank you very much for your patience. I know it's 10 minutes late. I costed you more time today. But guys, it is fruitful, I think. So guys, thank you very much. Yeah, thank you very much. And let me know if you have any questions, any doubts. Otherwise, we'll wind up, guys. Thank you very much from my side. Thank you. We can conclude this session now. That's it from my side.
Yes, Vikas, thank you. Thank you for the wonderful session. Guys, for you, is there any queries? Let me know in the chat box. I will try to address it. Or else we'll wind up the session for today and we'll meet you on the tomorrow, same time, same place. Okay, I think there is no more questions. Okay, Vikas, we'll wind up today.
Okay, guys. Thank you very much then. Thanks for your comments, ma'am. Thank you, guys. Yes, guys, we'll share all these things will be shared with you guys. So LMS and Chandana, there was some questions around like how do they get the access to this LMS and all. Can you
Yes,
explain
Vikas.
them?
I will share that registration link. Please fill that registration link. So we have a WhatsApp group. You can join there.
Okay, all right, guys. So Chandana will share this, guys. Okay, link. So you can take this link and you can fill this link. All right, guys. Then thank you very much. So guys, thank you very much. Dharam sir, thank you. Thank you for your kind words, and then see you tomorrow then. Thank you. Bye, guys. Good day.
Yeah, bye. Whoever not registered, so I shared the registration link. Please register in that registration link. I already shared. Okay, guys, we'll wind up the session. Thanks for joining. We'll meet you on the tomorrow, same